So Chapter 3, Part A. So we're going to look at the structure and properties of ionic and covalent compounds. In Chapter 2, we focused a lot on valence electrons. So valence electrons were the electrons in the outermost shell of an atom. These are the electrons that are available for bonding. So a chemical bond, by definition, is interaction between these valence electrons. This could be through transfer of electrons, or it could be through sharing, as shown in the picture here. The two types of bonds we're going to talk about this chapter are ionic bonds and covalent bonds. So ionic bonds are when electrons are being transferred. And we looked at this in Chapter 2. So when a neutral element either gains or loses an electron, you get an ion. So ionic bonds are results when the ions themselves are attracted to each other. For instance, if you have one element transferring or giving up an electron to another, what's going to happen is you're going to form a cation, a positively charged ion that has lost an electron, and an anion, which is a negatively charged ion that has gained an electron. So now you have a positive and a negative charge. And what we know of opposites charges is they attract. So ionic bonding is the transfer of electrons, and the resulting ions are now attracted to each other due to their opposite charges. Next, let's look at covalent bonding. So covalent bonding is not a transfer. This is when electrons are shared. We have two types of covalent bonding. We're going to look at nonpolar covalent and polar covalent. So what nonpolar covalent is when the atoms involved are sharing those electrons equally. For a polar covalent bond, this is when the atoms involved in the bond have an unequal sharing. What that means is one atom wants those electrons more. So they're not going to share them as much. This is going to result in one atom having a slightly positive charge, and the other atom, the atom that wants the electrons more, having a slightly negative charge. So let's first focus on ionic compounds, and we'll come back to covalent in a moment. So for ionic compounds, we said they're composed of ions. Ions being charged particles that form when an atom gains or loses an electron. Typically, this occurs between a metal and a non-metal. If you'll remember from Chapter 2, we saw when we were looking at ions that metals like to lose electrons, and so they form a cation, a positively charged ion. The nonmetals, on the right side of the periodic table, like to gain electrons. So if they gain electrons, they become negative, resulting in an anion. Well, since opposites attract, it would make sense that the cations and anions are attracted to each other, creating an ionic bond. So most often than not, we'll see metals and nonmetals forming ionic bonds. Now the bond is actually created due to the electrostatic forces between those positive and negative ions. In the example below, you can see the sodium atom, and all that is shown is the valence shell, the outermost shell. Notice there's just one electron in that shell. Well, that is due to the fact that sodium is an alkali metal, and all alkali metals have just one valence electron. So what happens is that sodium atom loses that one valence electron to another atom, in this case chlorine. The reason sodium wants to lose an atom is because it wants a full octet. So by getting rid of that one atom, it will now be in a noble gas state and be happy. Well, let's look at chlorine. So chlorine is the atom that's going to receive that electron from sodium. We're once again showing only the valence shell of the chlorine atom. You can see, if you count the electrons, that there are 7 green electrons in the valence shell. Now these 7 electrons, we can see from the periodic table that since chlorine is a halogen, all halogens have 7 valence electrons. Remember, everybody wants an octet. Everybody wants 8, just like the noble gases. And so, when sodium loses that electron and gives it to chlorine, that completes chlorine's octet, and now you can see The chlorine has 8 electrons, so it has a full outer shell and it is now happy. Since chlorine gained an extra electron, it now has a -1 charge. Since sodium lost 1 electron, it now has a +1 charge. So these opposite charges are attracted to each other, creating an ionic bond. Let's look at covalent compounds. Covalent compounds, we said, were when elements or atoms share electrons. So there's no transfer. There's no positives and minuses. So you can see in this first picture here, we have 2 atoms coming together, and in this circle here is them sharing their valence electrons. So with covalent bonds, the atoms themselves need to be in much closer proximity to one another. Now, there's 2 types of covalent bond. We mentioned that there was a nonpolar and a polar. So the nonpolar is equal sharing, and that's what you see in these diagrams to the right. You can see that the electrons are placed in the center between the 2 nuclei. Polar covalent bond would be where one atom has the electrons closer to its nucleus than the other, meaning it wants it more. It's a more electronegative atom. So let's look at an example of that. So in the diagram below, I have shown nonpolar covalent, which is the first example in blue here, polar covalent, second example in green, and then of course an ionic bond in red. So I have the different stages. So looking at a covalent bond, notice, so we have 2 elements, X and X. There is a pair of electrons right between them that they are sharing. Now this blue egg shape around them is the electron cloud, and notice it's very symmetrical because they are sharing those electrons equally. It is a nonpolar covalent bond. However, sometimes they don't share the electrons equally. So in the next picture, we have a polar covalent bond. Notice we have X on one side and another atom, Y, on the other. Now notice where the electrons are this time. They're still sharing, we can see, because of this egg-shaped green sphere here, but it's not quite equal, it's not symmetrical. That's because, if you notice, the electrons are closer to the Y atom. Why? Because the Y atom wants it more. The Y atom is more electronegative, so it pulls the electrons closer to it instead of sharing them equally. That's why you'll notice up top there's this little delta negative by the Y atom. What that delta sign means is partial. So it's partially negative on the Y side, making the X atom partially positive because it's not sharing those electrons equally. Now going to the other extreme, an ionic bond, notice there's a separation between that cloud. They're not sharing. They have fully transferred. So the Y atom has a negative charge and has both electrons to itself. The X atom has a positive charge because it gave an electron away. So how are we going to figure out the difference between a nonpolar covalent and a polar covalent bond? We can use the periodic table to predict electronegativity, and you'll actually get an electronegativity table which you can use the values to calculate. Here's that electronegativity table that I was referring to on the previous slide. So you can see it looks like a normal periodic table with the element symbols. However, underneath each element symbol are numbers that are not the mass number. So what these numbers are the electronegativities of each element on the periodic table. So we're going to use these to try to figure out whether a compound is polar or nonpolar. So to do that, we're going to use this equation here. So delta En is equal to, and those are absolute value bars, just like when we do our percent error calculation. We have En1 minus En2. So what this means is that delta En means change in electronegativity. Whenever you see a delta sign, it means change in. So to figure out the change in anything, you always need to take the final minus the initial. So what we're doing to calculate that is taking the electronegativity of one of the elements involved in the bond and subtract it from the electronegativity of the other element present in the bond. So an example, say we wanted to calculate the electronegativity of a boron-hydrogen bond. So we would find boron on our table and see that it has an electronegativity value of 2.04. We then would find hydrogen and see that it has an electronegativity of 2.20. Subtracting those from each other, we would get a negative number, but since we have the absolute values bars, we change that to a positive. So 0.16 would be the change in electronegativity. So what do we do with that number? We compare it to the scale shown here. So if the change in electronegativity falls between 0 and 0.5, it can be classified as a nonpolar covalent bond. In this case, the boron-hydrogen bond does fall in that range. It's 0.16. So it's less than 0.5 but greater than 0. So this would be a nonpolar covalent bond. If it was higher than 0.5, so between 0.5 and 1.9, it would be classified as a polar covalent bond because that's a much wider difference between its electronegativities. In order to get a polar covalent bond, this only occurs when we have two different atoms that have a large difference in their electronegativities, making one atom much more electronegative, thus wanting those electrons a lot more than the other atom. Notice we can do this calculation for ionic bonds as well. Generally, when we see a metal and a nonmetal, we classify that as an ionic bond. But some metal-nonmetal bonds can be classified as polar covalent using this calculation.